Hi everyone. In this video, we will see what is Markov processes and chain. See, in information theory, a source is something that emits sequence of symbols over time. So that symbol might be letter or signal. It depends upon the type of source what we deal with. Most simple sources, okay, are assumed to be memoryless. So we call it as a DMS, discrete memoryless source, meaning each symbol produced it independent of the previous one. For example, let's say that I have a source and that is emitting the symbols from this particular alphabet set. When I say alphabet set as A, B, C, then that source is capable of emitting only these three unique symbols. So the message constructed using these symbols might be A, B, B, C, and again A. So this might be a message. So now when one symbol is emitted by the source that is independent of the previous symbols. Okay, so it is not dependent. So this kind of source, we call it as a discrete memoryless source. But in real world system like languages and music, the next event depends on what just happened. And this is where this Markov processes comes in. So it is not independent. So the next symbol, what is to be emitted is present purely depend upon the particular current symbol. Okay. And what is a Markov process? In general, Markov process is a stochastic process where the future state depends only on the current state, not the past. So yeah, it depends on the current state, not the past state. So means let's take the same source. Let's say that the source is emitting some symbols. Okay, the next symbol, the future symbol to be emitted is purely based on the current symbol. So the first order, not the past symbols. So based on C, the next symbol. Let's say the next symbol emitted is A. And this is the current symbol. Now, the next symbol to be emitted is purely based on A, but not the past one. If that is the case, then we can say Markov process of first order. It depends upon only the last previous value, but not all the previous values. And what is the stochastic process means? Means it generates a random pattern, a random probability distribution, which means it can be analyzed only statistically, but not predicted precisely. So the next symbol to be emitted cannot be predicted precisely. I can't say this is the one is going to be, but I can put it statistically. It might be this or that, something like that. Okay. And when I say Markov chain of first order, it is a particular case of Markov process. So Markov process is a more general approach. When I say Markov chain, it is one particular approach under the Markov process. And in Markov chain, we will be having discrete collection of states or symbols. See, previously I was just saying symbol. Source emits symbol. And now let's try to relate that symbol to a state. So when I say state 1, state 2, state 3, and it is nothing but symbol 1, symbol 2, symbol 3. So each symbol will be mapped to a state. And when I say Markov chain, it will be having finite number of states or finite number of symbols. Okay. And then we can say Markov chain of first order. So again, Markov chain of first order means the occurrence of the next symbol purely depends upon the current symbol, or occurrence of the next state purely depends upon the current state. And again, so you will be having some set of states or set of symbols, and you put it as n symbol or n states. So let's say that you're dealing with three states or four states, let's say A, B, C, D, or the four states or four symbols. Okay, then the number is, the n is 4. So totally you have four different states or four different symbols. So if you're directly relating it to a source, and the source is emitting four symbol. Okay, so four possible states, something like that. Okay, let's try to decode this particular Markov chain diagram. So this is an Markov chain diagram. And this diagram is drawn using two shapes. One is a circle, another one is a arrow, directed arrow. Okay. And what this circle represent, they all represent a state. And you can see A, B, C, D are the states we have. You can even think of it as a symbol A, B, C, D. So totally four unique symbols. Fine. So if you see the other shape is the arrow mark, and that also comes with some weight. So what this indicates, transition. Okay, if the current symbol is A, next symbol might be B, and the possibility is 50%, something like that. And if the current symbol is A, there is another possibility that it can be the next symbol is also A, and the probability is 0.2, it's 20%. And from A, you also get a chance. So if the current symbol is A or the current state is A, then the next symbol or the next state can be D as well. And one more thing, like if you take all the outgoing symbol of this, sorry, outgoing arrow of this particular symbol, and if you take the probability and if you sum it, it must add to 1. So for example, we have state A, and this is one outgoing arrow, and this is second and third, and you take the probability of 3 and you sum it, you get 1. Not just A, you go on randomly select B, and B is what is this? So B has two outgoing arrow. And if you see the probability, it is 0.4, 0.6. It means like if your current symbol is B, then the next symbol possible might be A, 40% might be A, and then 60% might be D. Okay, so that's how this particular Markov chain diagram should be interpreted. So in a first order Markov process, we define a set of states and then transition probability. So these are set of states and then the transition probability, which tells us how likely the source is to move from one state to another state. So this is the source, and how likely from one state to another state it will be moving. Okay, let's go to this PPT, and here the first order Markov chain, the state transition probability is defined like this. So almost the same equation. So if you see the next symbol is purely based on the current symbol. So this is the symbol which is already emitted, and this is the symbol to be emitted next. So this is a kind of a time interval. So this is the first interval, and then this is the second interval. So at regular interval, symbols will be emitted, or regular interval that state transition takes place. Okay, so if we are transiting, the next state is purely dependent upon this particular current state. And if the state transition probability does not depend on time, then this Markov chain is called homogeneous. So what this means, so at the start, if this is the state transition probability, till the end, this probability will never change. It will remain constant. Okay, so if that is the case, then we call that particular Markov chain as a homogeneous one. So this probability, what is set, will never change. So right now, transition from A to B, if it is 50% or 0.5, then it will remain 0.5 till the end. It never changes. And from this given state diagram, we can represent a matrix, and we also call it as a transition probability matrix like this. And if you see, this transition probability matrix will be having n rows and n columns. And again, what is n? N is nothing but the number of state or the number of symbol. You can use this to interchangeably in the context where exactly you are dealing this Markov process. Okay, it can differ. So when I say n, so let's say when I say 4 state, then you will be getting 4 cross 4 matrix. When I say 5 state, then you will be getting 5 cross 5 matrix. And one more property is that, like, if you take the sum of a row, this sum of a row must be equal to 1. And that's obvious, like all the outgoing arrow probability, whatever you get, if you sum it, you get it to 1, right? The same thing here. Uh, So it means like the entire row will be having probabilities, and when you sum it, it must be 1. Okay, so that's how the transition probability can be represented. For this particular given diagram, how can we create or construct a transition matrix, let's say probability transition matrix. So we totally have four stages, right? Four states, right? So A, B, C, D. And let me put both in rows and columns as well. So from A to A, what is the probability? It's zero point 0.2. From A to B, what is the probability? It is 0.5. From A to C, no, it's 0. And A to D, it's zero point 0.3. Similarly, B to A, you can write. So B to A, it's 0 0.4. B to B, we don't have any transition. And B to C, also we don't have any transition. And B to D, we have 0 0.6. Perfect. So you have 0 0.2 plus 0.5 plus 0.3. If you sum it, it must be 1. Okay. So the sum of all the elements in one row must be 1. And this is how we can construct this particular transition probability matrix. Okay. And one more property is that, like when I say Markov chain, it is regular, and we should have only whole numbers in this particular matrix. Non-zero. All the values will be non-zero. So what that mean? So the transition matrix, what I have now here, or the Markov chain diagram, what I have here, it's not regular. And if you see there is one entry 0 present. So if there is one entry 0 present, then that Markov chain cannot be a regular. So what is an example for a regular Markov chain? I'll take one instance with two state A and state B. From state A, I can transit to state B as well as to itself. From B, I can transit to A as well as to itself. And I'll be giving some weightage. That's the probability, let's say 0.5, 0.5, and this is 0.4 and 0.6. Now, this is a regular Markov chain. So it means from any state, you have probability to reach all the other states. Let's say that you are having 10 state, and from one state, you will have some probability to reach all the other 9 states. If that is the case, then that Markov chain is a regular Markov chain. So also you can say if you construct a transition probability matrix, you will not have any zero values. All will be a positive number. Okay, based on this, we have one sum. Let's do that particular problem now. Yeah, this problem is all about finding the steady state probabilities. Means this is how the transition probabilities are given. Okay, when a system is running for a long time, for a long number of steps, then what is a steady state? Okay, so if I relate it to source, let's say that we have a source and then that source is emitting two symbols like S1 and S2. And this source is emitting, let's say, 1000 symbols. So at the end of 1000 symbol emission, how much symbol would be S1 and how much symbol would be S2? So with this particular probability, we can define that number also. It's not exactly precision, but yes, statistically we can represent. So or at the end of 1000 symbol emission, S1 was this much and S2 was this much. And for that, we are going to solve this particular problem. We find the vector. So when I find the vector, then it gives probably this must be the number of S1 and this must be the number of S2s. Let's try to decode this particular problem. So given homogeneous and regular Markov chain, so that is what we discussed. So when I say homogeneous, it means the probability what is given will never change over time. So at the start till the end, the probability will remain same. And a regular Markov chain. So when I say regular Markov chain, it means you'll not have any zero values in your transition matrix, transition probability matrix. So from one state, you have at least some probability to reach any state. Okay, and this particular uh, Markov chain diagram has only two states, state 1 and state 2. You can even represent it as A, B. If in case your source is emitting two symbols like A and B, then you can mention it as A and B or state 1 and state 2, whatever it is. Okay, now we need to just first produce the transition probability matrix. And we will first create a transition probability matrix, and then we will go and find the vector W. So you can name the vector as pi also. It's totally depends upon you, one variable. So we are going to denote vector as W, and we will identify vector. So what that vector means, steady state probability. So when we run this for a long time, how much time the system was in state one and how much time the system was in state two, or how much time system produced symbol A and how much time the system produced symbol B, like that we can come to know. So let's get started. So first we will create the probability matrix, transition probability matrix, that is P. Okay. So we totally have two states. It means like you will be getting 2 cross 2 matrix. State 1 to state 1, it is 0.8. State 1 to state 2, it is 0.2. So when you sum these two, it is coming to 1. Next, state 2 to state 1, it is 0.4. State 2 to state 2, it is 0.6. So this is the probability matrix what we got. Next, we need to identify vector. So for identifying vector, we have a formula, that is this one. Okay. So W dot P is equal to W. And what is this W here? The number of states. So we totally have 2 states here. And W1 and W2, when you sum it, it must be 1. Again, this is probability, right? So you're trying to identify the steady state probability, right? So steady state probability means you have 2 states. And when you sum those 2 states, it must be, the probability must be 1. It might be 0.4, 0.6, 0.3, 0.7, whatever it is. So the sum must give it to 1. Okay, so let me consider this as an equation 1. And let's try to solve this particular thing. So this can be expanded as totally we have 2 states, right? So the state is W1, W2 gets multiplied to the probability what we have, that is 0.8, 0.2, 0.4, 0.6 equal to, again, you totally have 2 states, W1 and W2. Let's get 2 equations from this particular representation, that is W1. Okay, or so you take the first row and then the first column here and equate it to W1. So W1, that is 0.8 W1 plus, so this must be W2. Yeah. And this is 0.4 W2 is equal to W1. Either you can even write it this way also. W1 is equal to 0.8 W1 plus 0.4 W2. And let's get the second equation. For this, again, you have only one row, and then we consider the second column here. Okay, I'll write it this way. So W2 is equal to 0.2 W1 plus 0.6 W2. Done. So now let's try to solve this equation. So we totally have 3 equations right now. So this is number 2 and number 3. Okay. Either you can take 2 or 3. Let me take equation 2 and I'll solve that equation 2. That's W1 is equal to 0.8 W1 plus 0.4 W2. This can also be written as like this 1 into W1 or W1 the same, right? So what I'll do, 1 into W1 plus, not plus, I'm bringing this term towards the other end before equal symbol. So it means minus 0.8 W1 is equal to 0.4 W2. So it is 1 into W1 minus 0.8 into W1 is equal to 0.4 W2. Then I can write it this 1 minus 0.8, it is 0.2 W1 is equal to 0.4 W2. Now when I say W1 is equal to, so this I'm bringing to the other side, so it will come to division, 0.4 division 0.2 W2. 0.4, when you divide it by 0.2, you will be getting 2. That is W1 is equal to 2 W2. Okay, let's say that this is my fourth equation. And now let's substitute this equation 4 in equation 1. So we have equation 1, that is W1 plus W2 is equal to 1, right? So we'll substitute in that 4 in 1. So 4 is this, W1 is equal to 2 W2. And equation 1 is W1 plus W2 is equal to 1. So now I have got the value for W1. So it is 2 W2 plus 1 W2 is equal to 1. And that will sum up to 3 W2 is equal to 1. And W2 is equal to 1 by 3. So when I say 1 by 3, we'll be getting 0.333. So you can even consider this as equation number 5. And you can substitute this 5 in 1 or 5 in 4. You get the final answer for W1. So W1 is equal to 2WT. So that is according to equation 4. So I'm going to substitute 5 in 4. Okay, according to 5, W2 is 0.333, right? So it is 2 times 0.333 is what is W1. Then that you might get it around 0.667. So this is W1. So at the end I can say W1 is equal to 0.667 and W2 is equal to 0.333. And if you sum this, you get it to 1. Yes, that is expected. But now what this means, so the system will stay in the state S1 or W1 at this particular probability and state 2 with this particular probability. So when source is emitting 1000 symbols, out of 1000 symbols, 667 symbol might be symbol 1, and then 333 symbols might be symbol 2.